Hi, thank you so much for joining. Rashid here. We are into week 8 of the STA training, and I've been doing a lot of practical demos of the STA tool. And one of the demo was on clock gating timing. And I think there are still some confusions. So let's get back to the whiteboard, and I'm gonna show you the setup time and hold time of clock gates. Okay, so let's get started. So this is the simple circuit I drew, and I also created a netlist for it and brought that into the STA tool. So we will look into this circuit, and here you can see. So we have flip-flop and flip-flop. So there's a flip-flop to flip-flop timing here, and then U1 is an AND gate. I mean, it doesn't have to be an AND gate, but just for this design, A and B are ANDed together from the inputs go into the first flip-flop, and there are two buffers in between the two flip-flops. Output of the last flip-flop goes outside the design. Okay, the clock of U3 comes from an AND gate. An AND gate, one input is clock, the other input is an enable signal. And the clock pin of U6, it comes from an OR gate, and one of the input of OR gate is clock, same one that goes to AND gate. The other input is enable, which is also shared between the two. Okay, so let's look into the setup timing and hold timing of the enable pin, because that is the endpoint, right? So if you remember, we are checking timing to all the endpoints. And what are the endpoints here? So one endpoint is this flop D pin. These are not endpoints here because data is here, data is here. They just pass through this. Then this is not an endpoint. Endpoint is what? Flip-flop input. So this U6D, U3D, output ports are endpoints. Input ports are not endpoints. What are they? Those are start points. But here are this enable pin, where one input is clock, other input is enable. This is also an endpoint. So these two are endpoints too. And clock A2 or clock A1. These are endpoints, because this data need to be checked whether it's stable before the positive or negative edge of the clock comes in for setup and hold time. And we will look into right now what are those edges. But just wanted to make sure these are the two endpoints too. So how many timing paths we have in this circuit total? Okay, one timing path is here from A input port to D. Do we have a timing path from B to D? Yes, we do. So there are two paths here. Their start points are different, end point is the same, but their through points are also different. So this one goes to A1 to Z, this goes from A to Z. Okay, so next timing path is, this is pretty obvious, from here to here. Actually, whenever I say start point, you should see, okay, clock comes here, here, this is your launch, and capture, what is capture? Clock comes here, and this is your capture. Okay, what is, so 1, 2, 3 paths, and this one, this is the launch, and capture is outside, which we use virtual clock, which we talked about that, right? So this is a path, so 2, 3, 4, and then we have 5 and 6. So for this one, what is the launch? Launch is on this one, enable, coming in, and it's coming in from the outside world. So just like this one. So this is your data, and there's a launch clock is on a virtual clock, and capture clock is this one, the same as this one. So 1, 2, 3, 4 to 6. Did I do it right? Yes, 2, 3, 4, 5, 6 timing path. Make sense? So before we start looking into clock gating setup and hold time for both of these, quick on the flop to flop. So if you look at this flop from this one to this one, this is a rise edge, this is a rise edge. So this clock, this pink one is at U3CP, it's coming here, and this one is U6, which is this one. So data is launched on the rise edge of this clock, and setup edge, well, it's launched here, but we want to make sure that it's captured on the rise edge of the capture clock a cycle later on. When we need to ensure that the data path, the delay from here to here, plus some setup time, that data needs to be stable before the rise edge. This data arrives before that. So it meets the setup time, and overall setup check is met. So whenever I choose setup timing is from this side to this side, but there is a setup time which comes from capture flip-flop, and it comes from the standard cell library, right? So that is the setup edge, rise to next cycle rise. Okay, for the flop to flop, what is the hold one? Hold is launch is the same, and capture is where. And then of course, you always remember that, okay, capture edge hold time is, there's a hold time coming from the flip-flop, right? But it needs to be certain time stable here after the rise edge of the clock. But how much is it? It's from here to here. Okay, so what we want to make sure, this is sometimes people get confused. People understand, okay, what is hold time? Hold time is that, okay, after rise edge of the clock or whatever the active edge of the clock, the data need to be stable certain time after that, so that it is not taken during that uncertain time. But it's also important that the edge involved are launched here. You want to make sure that data that is launched here doesn't come too fast to this. So data launch here doesn't arrive too fast in this deep end that is captured here. We don't want this race condition. So we want this data to be long enough that it passes this window the whole time of this, so that's not captured here, is actually sits there and is captured here. Make sense? So that is flip-flop to flip-flop setup and hold time. So you need to understand that before you go into AND and OR gate. That's why I did that. But if you already know, let's get to our AND clock or OR clock maybe. Yeah. So this is our timing path. So I just have taken out the OR gate. So this is this OR gate here. Clock is the input pin. The other one is enable. Enable, since it's coming from the port in this case, I mean, it can come from another flip-flop in this design too. But let's say it's coming from the output, input port, sorry, from output side, from the outside into the input ports. But eventually it's some another design is driving. And let's say we are talking about this block, the inputs are driven by another block on the same chip. So this flip-flop, this dotted line circuit is not present within this circuit, within this design, is present outside into another design at full chip. But this is somewhere that enable is launched. Okay, so the launch path is this, capture is this. Now try to understand the clock gating in the case of OR gate. So property of OR gate is when one of the input is 1, output is 1. When one input is 0, then it depends whatever the other input. So for example, in this case, we have, this is the truth table for it. So inputs are clock and enable, and this is output, right? When clock is 1 during the high phase, right, then whatever is the input on enables, it has no impact on the output. If it's 0, output is 1. If it's 1, output is 1. That's what I'm putting across, don't get. But when clock is 0, if enable is 0, output is stay at 0. Enable is 1, right? then whatever clock is 1, which is 1. So enable is controlling only when, enable is controlling the output only when clock is 0. So in other words, we can say that the negative level, low level of the clock is what we are controlling. The high level we cannot control because there's no impact. I mean, output will always be 1. Make sense? So in a way, this is how N and R clock behaviors are different for clock gating. So, but let's look into, if now this is our timing path, okay, what are the setup and hold edges? So again, in our case, this flip-flop is outside, but this is our launch, assuming it's a rise edge flip-flop. So our launch is this clock, this stop clock is at here. This is our virtual clock, and this capture clock is here. Make sense? So a timing path, we define clock here, we define clock here in our timing constraints, right? It's just like a stimulus. You need to tell the tool what is clock period. So for example, here I'm saying it's 10 nanosecond time period, which means its frequency is 100 megahertz. So launch starts here. Okay, we're talking about setup timing check. Launch is here, and when it's launch here, this one, we want to make sure that before the low level of the clock comes in, that this data enable is stable. So there is also a setup time right before this. Okay, and we don't want enable signal to, we want it to kind of ideally stay like this. Okay, but it starts stable here. If it's not stable here, goes into this, we will have kind of a glitch in our output clock. You understand that? For example, here, if it goes initially here, now clock is 0. If enable is 0, clock stays as 0 at the output. But if enable is 1 for very small time, clock will go like this. So we want to make sure our clock is stable here. Okay, so that is the setup check. So keep in mind, the setup is not from 0 to 10. Setup is 0 to 5 nanosecond. Now what is the hold? Hold is easy in this case. Why? Because it's the same thing as in flip-flop to flip-flop case. We want to make sure this change over here is not captured during this cycle, or you can even understand it better here. Whenever this data stays stable, right? So that this data, for example, on the next cycle, whatever enable comes there is not, changes happen, is not captured here. So setup is here, hold is there. Make sense? Hold is a little tricky here. I think setup is easy. Again, hold is, you want to make sure you don't have a race condition. The data that you launch here is not too fast that is captured right now here and part of this change here. You want to keep it a little bit delayed so that whatever change that happens, eventually it happens during this time. So this is could be the problematic situation for race condition. So hold we want to ensure is from 0 to 0, setup as 0 to 5. Make sense? All right. Let's go to our AND gate now. Similar picture. Now we're talking about this AND gate. So your AND gate comes here, similar picture. This is your capture clock and your enable coming from outside, and that is the outside flip-flop that is launching it. We are assuming it's a rise edge flip-flop. Okay, the AND gate has the feature that when one of the input is 0, output becomes 0. So for in this case, when clock is 0, doesn't matter what enable is, output will be 0. When clock is 1, if enable is 0, output is 0, when enable 1, 1. So in other words, enable is controlling the output only during the high phase of the clock. which is this one that I highlighted. By the way, the previous one highlighted was this is the active. In the AND case, this is active. So when clock is 1, if enable comes 0, output clock shape will be different. You understand that? Right? So, okay, let's look into his interesting part. Let's look into the setup edges and the hold edges. So, setup edge is from when launch is both common between the other case and this case. So, launch comes here because this is rise edge, right? That is launch here. Now, when it's launch here, okay, you want to capture on the next cycle. You're not capturing on this one, right? So you want to make sure that it is kind of stable before that edge comes. Ideally, a little bit setup time before that. So setup, in this AND case, we have a whole cycle, right? But for hold, okay, what is the scenario? Even though it's written here, do you understand? It's a launch here, capture is here. Why? Because once this data is available, you don't want to change during this phase. If you change here, it will go into changes here. It will start impacting the output. So there is a window here from here to here. That's where your data can change. But during this half cycle, we don't want enable signal to change, right? So you can see that in this case, a hold time is problematic because that seems like you need, if you need to kind of delay your circuit, you need to put some delay cells here. In this OR gate, your setup is half cycle. You don't have much time. Now, I'm not talking about a clock tree here, but ideally when clock comes here, there are clock tree built on it. Now it depends. This clock will typically not be balanced like the other flip-flops. It will somewhere sit in the middle or somewhere along the line. So delay is already pretty short here. This can be a problem depending on your clock or your circuit there. This kind of independent of the clock. Well, if the clock period is bigger, you will have to put more delay cells. So it kind of depends, the whole fixing depends on that too. So there is one problem, and the other problem you can see is there could be a glitch, crosstalk glitch can happen on enable. And during this time, if enable shouldn't, but maybe a little bit noise on the enable signal might be enough to propagate to the output and make a complete swing at the output. Okay, so let's finish this video here. In the next video, I will talk about some of the problem with this circuit and the OR circuit, and why we use actual clock gate and what is different in clock gate. And we will also look into setup and hold time when an actual proper clock gate is used. All right, so see you next time. Bye.